Good evening, everybody. So today we will be discussing electrochemistry. So electrochemistry involves study of electrochemical cells. And there are two types of electrochemical cells, galvanic cells and electrolytic cells. Today we will be concentrating or focusing on galvanic cells. So first of all, what are galvanic cells? These are devices which use a spontaneous redox reaction to produce electricity. So these are electricity producing devices like common battery, pencil cells which we use, car battery. They all are galvanic cells and they convert chemical energy to electrical energy. Okay. And they are made by connecting two half cells. Any galvanic cell will be made up by connecting two different half cells. One half cell where oxidation will occur, another half cell where reduction will occur. The half cell where oxidation will occur will always be called as anode. The half cell where reduction will occur will be called as cathode. And in our notation, cathode will always be written in left and anode, cathode in right, anode in left. Okay. So this terminology should be clear to us that salt bridge के left में जो लिखा है वो anode है. Whatever is written in right of salt bridge, that is cathode. At cathode, reduction will occur. At anode, oxidation will occur. So this is basic definition. What is a galvanic cell? It is a electricity producing device. So next thing, now let's understand how we will calculate EMF produced by a galvanic cell. So first of all, we should understand for any half cell, see, in any half cell, two oxidation state of an element are involved. Okay. and there is always a equilibrium between these two states. Let me take a very simple example of a half cell. Let's take this half cell. We have taken a zinc plate and we have dipped it in a solution of Zn2 plus ion. Now this is a typical half cell. Here the two oxidation states of zinc involved are the elemental state of zinc, where its oxidation number is 0, and the second state involved here is Zn2 plus, where the oxidation number is +2. So these two oxidation states are involved here. Now what will happen at this boundary, at the interface of metal and solution? Two things will be happening. One, the metal atoms will have a tendency to go in solution as their cation, leaving behind their electron. Means the first thing I am saying, zinc atoms will have a tendency to get converted to zinc ion, which goes in the solution, and the electrons are left on the plate. This is one thing which will be happening at this interface. Second thing, zinc ion in the solution will have a tendency to take electron from the plate and get converted to zinc atom. Means this reaction or this tendency will also be there. So these both reactions will be occurring at the surface simultaneously, and hence very quickly a equilibrium will be established between the two oxidation states of this element. So this equilibrium will be established. And this equilibrium may be shifted in right direction or in left direction, depending on the oxidation states and the element involved. Okay? In whichever direction it is shifted, let's say for discussion I say this equilibrium of zinc is shifted in right direction. Means what I am trying to say when I say shifted in right direction, that the first reaction is happening more than the second reaction. Means overall in net zinc atoms are getting converted to zinc ions. So in that case, when more zinc atoms are getting converted to zinc ion, they will leave behind their electrons on the plate. And these excess electrons on the plate will create a negative charge on the plate. And more zinc ions will go in the solution. And that will cause a positive charge to be developed in the solution. Now we will see here, we are seeing here that two charges have developed. Two layers of charges are developed. And these charges are opposite. One on the plate, another in the solution. So two layers of charges have developed. The potential difference between these two layers of charges is called as electrode potential. So for any half cell, there will be two oxidation states involved of an element, and such a equilibrium will be established between those two oxidation states. Due to development of these two oxidation states, we will see, due to this equilibrium, we will see development of two layers of charges, opposite charges, one on the plate, another in the solution. And the potential difference between these two layers of charges is called as electrode potential. Now, how do we measure electrode potential? See, electrode potential is measured with respect to standard hydrogen electrode. Means we connect any half cell to a hydrogen half cell, and then when we measure the potential of that galvanic cell, That will give us the potential of that half cell, because for hydrogen half cell, by convention we define the electrode potential of hydrogen half cell to be 0. So what we are saying, by convention we are defining that EMF of E naught of standard hydrogen electrode, this by convention we are defining as 0. Okay. So now अगर मुझे किसी भी हाफ सेल का EMF पता करना है, तो we will connect it with a standard hydrogen electrode, make a galvanic cell, because whenever we connect two half cells we get a galvanic cell, and we will measure the EMF of that galvanic cell. EMF of that galvanic cell will give me electrode potential of that other half cell which was connected to hydrogen. And this brings us to the main formula, that E naught of any galvanic cell is given as E naught of any galvanic cell is given as E naught SRP cathode minus E naught SRP anode. Standard reduction potential of cathode minus standard reduction potential of anode. Okay. So like, for example, let's say we are given these two half cells and their EMF values, their standard electrode potential. For zinc, it is given to me as minus 0.76 volt. For copper, it is given to me as plus 0.34 volt. So first of all, let's understand what does this minus and plus means here. See, all these values, you should always remember, these all values are always with respect to standard hydrogen electrode. Okay. So what is this minus 0.76 meaning? As you can see the notation, Zn2 plus 2Zn. This is reduction potential of zinc given to me. Correct? And for hydrogen, the reduction voltage is 0. For zinc, it is negative. Means the reduction tendency of zinc is lesser than reduction tendency of hydrogen. What is the reduction reaction for hydrogen? For hydrogen, I can write the reduction reaction like this. And what will be the reduction reaction for zinc? This. So what is this negative value telling me? Understand? This negative value is telling me that the tendency of this reaction is lesser than this reaction. Correct? Or I can say that Zn2 plus is more stable than H plus. Zn2 plus does not want to go to Zn. as compared to H plus wants to go to H2. It means Zn2 plus is more stable than H plus. This is the meaning of this negative sign. Versus like for copper. For copper, the reduction voltage is given to you as 0.34. So here what does this means? The reduction reaction of copper is Cu2 plus 2 electron goes to Cu. And you can see the reduction voltage is positive, greater than hydrogen. It means this reaction has a higher tendency to happen as compared to this reaction. So what I can say now here is Cu2 plus is lesser stable than H plus. Okay. So the concept of negative or positive sign is clear. Okay. Now, next thing. So this is what we wanted to understand. Standard reduction voltages say what we can deduce. Now, as far as calculating E naught of any cell is given there. So we had written this formula that E naught cell is SRP cathode minus SRP anode. Reduction voltage of cathode minus reduction voltage of anode. Now there might be this confusion in many of your mind that what will be cathode and what will be anode? How will we decide who is cathode and who is anode? E naught values so will be given to you in the problem. That data will be given. But how to decide which is cathode, which is anode? So for that, please remember, first point, if cell notation is given to you in the problem, the notation proper with salt bridge is written, then half cell written in left of salt bridge is anode, half cell written in right is cathode. Okay. So if the notation is given, you will properly read the notation and then understand. If the notation is not given, so if you are not given the cell notation, then what you will do? Then the half cell having higher SRP value will be cathode. So whichever half cell has higher SRP value, that will be cathode. Okay. So if the notation is given, they have already given you what is cathode, what is anode. If the notation is not given, then you will decide like this. So for the same example of copper and zinc, suppose I have given a problem like this. Find E naught cell of Cu2 plus salt bridge Zn2 plus Zn. And we are given the reduction values SRP Zn2 plus Zn minus 0.76 and Cu2 plus Cu 0.34. So now what I can see in this problem, salt bridge is this double vertical line. Left to salt bridge is copper half cell. Right to salt bridge is zinc half cell. Here notation is given to me. So I know zinc half cell is in this notation is cathode. Copper half cell is anode. So I will calculate E naught cell as E naught SRP cathode minus E naught SRP anode. Cathode here is zinc half cell, SRP value of zinc minus SRP value of copper. So I will get minus 0.76 minus 0.34, that is minus 1.14. But suppose the same problem, a similar problem was given to me like this. A copper half cell is connected with a zinc half cell. Find E naught of resulting cell. So now here we can see we are not given any notation. Okay. And I see the E naught values, E naught SRP values. I see that SRP value of copper is greater than zinc. And hence I decide whenever I will connect a copper half cell with zinc half cell, copper will want to act as cathode and zinc will want to act as anode. So now I will find E naught cell as SRP cathode minus SRP anode. And now cathode I will decide to be copper half cell and anode I will decide to be zinc half cell. So now this answer will become 1.1 volt. Okay. So this is regarding calculation of E naught cell. Is this clear? So 2 points which you need to remember clearly. Again, I am coming to that, showing you. If notation is given, follow the notation. Half cell written in left to salt bridge is anode. Half cell written in right to salt bridge is cathode. If cell notation is not given, then the half cell having higher SRP value is cathode. Again, as we can see in this example, in both questions, we were connecting a zinc half cell and a copper half cell, and their SRP values were given to us. In first problem, we were given a cell notation written. And how was that cell notation given? Zinc half cell was written in the right of salt bridge. Copper half cell was written in the left of salt bridge. So I follow the notation and I say zinc half cell is cathode, copper half cell is anode. Okay. But in contrast, in the second problem, what happened? In the second problem, we were not given any notation. We were just said that a zinc half cell and a copper half cell are connected. So in such a case, whichever half cell has higher reduction voltage, that we will decide as cathode. So in second problem, I decided cathode to be copper half cell because its reduction voltage was higher than reduction voltage of zinc half cell. Okay. Now, the next thing what we can discuss. So this was E naught cell, calculation of E naught cell, and E naught cell, you should know. E naught cell is EMF of the cell when so E naught cell is EMF of the cell when active masses of all involved species is 1. Means if there are any ions involved in the redox reaction, their molarity should be 1 molar. If there is any gas involved in the reaction, partial pressure of that gas should be 1 atm. Okay. Yeah, 1 bar also. Both go. So E naught is EMF only when all active masses are 1. But it is not necessary that whenever we will construct a half cell, that active masses will always, we will keep 1 or they will remain 1. They might change or we might from starting put a different value. So in such cases, then to calculate EMF of cell, we use an equation which is called as Nernst equation. Nernst equation says E cell is equal to E naught cell minus 0.059 by N log Q at 298 Kelvin. So this is Nernst equation. Here Q stands for reaction quotient, means Q will be equal to active mass of C raised to C D raised to D by A raised to A B raised to B. If the redox reaction of this cell is this. For this reaction, this is how we will calculate Q, and N is N factor of the reaction. Okay. So this equation is called as Nernst equation, by which we will calculate EMF of the cell if active mass of involved species is not 1. Okay. So let's understand how we will apply Nernst equation by a few examples. No, this is not equilibrium constant. Please understand. Equilibrium constant में these are active masses at equilibrium. If these are active masses at equilibrium, then this is equilibrium constant. But if these are active masses at any instant, at starting or anywhere during the reaction, then this ratio is not called as equilibrium constant. Then it is called as reaction quotient. Okay? Yes. So now let's see how to apply Nernst equation. So let's take a very simple example to start with. Let's say we are given this cell Zn2 plus 0.1 molar salt bridge, Cu2 plus 0.01 molar Cu. Okay. Now, and E naught value obviously are given to you. Zn2 plus Zn minus 0.76, Cu2 plus Cu 0.34. Yes. So now, what are the steps to apply Nernst equation? Let's see Nernst equation once again. If we have to calculate E cell, what all things we need? First of all, we need E naught cell. E naught cell we have learned how to calculate. This is anyway a constant number. Next thing we will need is N factor. So somehow we have to calculate N factor from the given reaction or given problem data, and the next thing we need to calculate is Q. तो ये तीन चीजें निकालनी है. These three things we will have to calculate to find E cell. Let's come back to this problem and see. E naught cell, directly I can see notation is given to me. Copper half cell is written right, zinc half cell is written left. So copper is cathode, zinc is anode. E naught cell I write so that will become 1.1 volt. Okay. Now, next thing, for N factor and Q, I will always suggest you that first you should write the balanced reaction for this galvanic cell. So here, cathode is copper half cell. Reduction will be happening there. So at cathode, this will be the reaction. Reduction, higher oxidation state to lower oxidation state. Between the two states, this is anode. Oxidation will be occurring here. From lower oxidation state to higher oxidation state. So the reaction at anode will be this. And hence we can see overall reaction here will be Zn plus Cu2 plus goes to Cu plus Zn2. And we can see the electrons involved in both half reactions. Both sides number of electrons involved are 2. So it clearly tells us that N factor of this reaction is 2. So now we have sufficient information. Now we can proceed to apply Nernst equation. So how we will write E cell now? E naught cell we have already got 1.1 by 0.0959. N factor we have got 2. log of, let's see the products. First product is copper, solid copper, and we know active masses of solid is always taken as 1. So this is not going to come. Next product is zinc ions. So I will have to write molarity of zinc ions here. Stoichiometric coefficient is 1. Now let's come to reactant side. Solid zinc, active mass 1. Copper, we put active mass of copper. So now just we can substitute the values to get our final answer. Zinc ion molarity is given 0.1. Copper ion molarity is given 0.01. So this will become 10. Log 10 is 1. So 1.1 minus 0.059 by 2, which we can calculate. So how to apply Nernst equation? What will be the steps involved? I hope it will be clear by this example. Let's take one more example to understand to apply Nernst equation. Let's say we are given a half cell like this. Platinum, Cl2, 2 ATM, Cl minus, 0.1 molar, salt bridge, Cu2 plus, 0.2 molar, Cu. Okay. So let's say we are given this cell and we are asked find E cell, and the E naught values, yes, they are given. Let's say reduction value of copper given to us as 0.34. Okay. And reduction value of chlorine is given to us as, let's say, 1.36 volts. Okay. So yes, first step, let's find E naught cell. What will be E naught cell? Copper is written in right. It means copper is cathode, copper half cell, and chlorine half cell is anode. So reduction voltage of copper 0.34 minus reduction voltage of chlorine 1.36 volt. So this we get as minus 1.02 volt. Okay. Now, N factor and Q, let's write the reactions. Reduction reaction at cathode, Cu2 plus 2 electron goes to Cu. Higher oxidation state से lower oxidation state. Oxidation at chlorine half cell means lower oxidation state to higher oxidation state. यहाँ इसकी oxidation state है 0, इसकी है -1. So the lower oxidation state is -1, higher oxidation state is 0. So the reaction here will be 2Cl minus goes to Cl2 plus 2 electrons. Again, as we can see, N factor is 2. Both 2 electrons are involved in cathode and anode. And now let's calculate E cell. E naught cell we have already got. minus 1.02 volts minus 0.059 n factor to log of. Let's write log Q. For this half cell, product is copper solid, which is active mass is 1. For this half reaction, product is chlorine gas. So I will take partial pressure of chlorine gas. Here, reactant is copper ion. So molarity of copper ion multiplied by, here reactant is chlorine ion, Cl minus, and its stoichiometric coefficient is 2, so square. So now I substitute the values, minus 1.02. This you can take 0.06 also, does not matter. Will give you almost same answer. Partial pressure of chlorine gas 2 atm, copper ion 0.2 molar, Cl minus square 0.01. Correct? So how much will this become? This will become 10 raised to 3. Log of 10 raised to 3 will be 3. So this becomes minus 1.11 volt. So here you can see in this example, I have taken such that gases, ions are involved together. And this is how we can apply Nernst in this. One more example, let's take. Here we were applying Nernst on a complete galvanic cell. We could also apply Nernst only on a half cell. Okay. So how to apply Nernst only on a half cell? Suppose we can take suppose an example like this, that we are given E naught of MnO4 minus Mn2 plus. This E naught, let's say, is given to me as 1.51 volt. Okay. And let's say we are asked to find E of this half cell at pH equal to 3. Okay. Now you might think at first instance, how is pH going to affect here? H2, H we can't see anywhere. So yes, first let's write the half reaction. So here, if we write the reduction reaction, in MnO4 minus, oxidation state of manganese is +7. And in Mn2 plus, oxidation state is +2. We have to write a reduction format. So higher oxidation state to lower oxidation state. So MnO4 minus goes to Mn2 plus. But this is not yet balanced. Oxygen on both sides is not balanced. Charge on both sides is not balanced. Oxidation number is changing by 5, correct? So there should be involvement of 5 electrons here. So let's now completely balance it. So first of all, oxidation number is going from +7 to +2. So there definitely need to be 5 electron here. Okay. Next, let's go on balancing charge. So how many electrons, how much negative charge we can see on this side? -6. Here we can see +2. So a difference of 8 in charge. As the pH value is suggesting, pH is 3, that this medium is definitely acidic. So we have H plus ions with us. So to balance charge, we add 8 H plus ions. Now charge is balanced. And next, for balancing hydrogen and oxygen, we add 4 water here. Okay. So this becomes our balanced reaction. And now let's apply Nernst. So now if I apply Nernst, how will I give E cell? E naught cell is given to me. E cell या half cell. E लिख लेते हैं केवल. This is not a complete galvanic cell. E will be equal to 1.51 minus 0.059. N factor of this reaction, as you can see, number of electrons involved, 5, log, let's write Q. We are only given pH 3. We are not given anything about molarities of other ions. So in this case, molarities of other ions we will assume to be 1. So this Mn2 plus molarity we will take 1. Water anyway is solvent and its active mass will be taken 1. MnO4 minus we will again take 1. But H plus, pH is 3, means molarity of H plus is 10 raised to -3. So now if I put that molarity of H plus, 10 raised to -3, and the stoichiometric coefficient of H plus is 8. So this will become 10 raised to -24. Hence this log will become +24. So the E value will come out to be 1.51 by 0.059 by 5 into into the question was like this, that which of the EMFs depend on pH, and you are given 4 options like this: platinum, Fe3 plus, Fe2 plus. And we are asked that which depends on pH. So how will we proceed in this? Which will depend on pH? Whichever is whichever has H plus in its balance the action. So now let's write the balance reactions. For this, what will be balance reaction? In oxidation form, platinum is written on left. So Fe2 plus goes to Fe3 plus electron. This in oxidation form. Just now we have written this reaction. Mn2 plus 4H2O will give MnO4 minus plus 8H plus 5 electron. This in reduction format, this is AgCl plus I electron goes to Ag and Cl minus. Oxidation in fluorine, F minus goes to F2 and 2 electron. Now here, in which of these half reactions is H plus coming? Only in option B. So that will be our answer. So then means to 22. Okay. So Nernst equation application is clear, I hope, to everybody. Next, we can move to the other terms related with EMF of a cell. That is equilibrium constant and Gibbs free energy. So what we can see here, one relation, delta G naught of any reaction can be given as minus NF E naught, where N stands for N factor, N is N factor, F is Faraday, that is charge on 1 mole electrons, whose value we take as 96500 coulombs. Okay? So this is the relation of E naught with delta G naught. And with equilibrium constant also, an important result, log K is equal to N E naught by 0.059. And same N factor, E naught of the cell, 0.059 is anyway a constant. So these are relation with equilibrium constant and delta G naught and E naught. So let's take up now some examples here. So let's take a few PYQs only. So let's take a problem like this. This cell was given and it was asked that delta G of this will be negative if, and the options given to us was C1 equal to C2, C2 equal to C1 by root 2, C1 equal to 2C2, and C2 equal to root 2 C1. So we can see this problem is the application of Nernst equation. We have to find some relations in EMFs. And we are asked, when will delta G be negative? Now, delta G we know is minus NFE. So for delta G to be negative, E should be positive. Okay. So for delta G to be negative, E should be positive. So let's see under which condition E of this will be positive. Let's write E naught cell first. Here you can see on cathode side as well as anode side, both sides the half cell used is copper half cell, correct? Such a special cell is also known as concentration cell when both half cells used are same. So E naught cell will be E naught of Cu2 plus Cu minus E naught of Cu2 plus Cu, and which will obviously be 0, which is another very important property of concentration cells, that their E naught cell is 0. Once again I am repeating, what is a concentration cell? When both half cells are same. Such a galvanic cell is called as a concentration cell, and E naught cell of such a cell is always 0. Now let's write the reactions. Reaction on anode side will be Cu goes to Cu2 plus, whose molarity is C1 plus 2 electron. The reaction on cathode side will be Cu2 plus, whose molarity is C2 plus 2 electron goes to Cu. So now if I apply Nernst, E cell will be given by 0 minus 0.059. N factor of the reaction is 2 log of. Here product is solid copper, active mass 1. Here product is this copper ion, whose molarity is given C1. Reactant side here C2, and here solid. So this becomes our effective equation. We want E cell should be positive, and there is a negative sign here. Means this entire log term should come out negative. If this log term comes out negative, this entire RHS will become positive. And for log to be negative, the fraction should be less than 1. So for log to be negative, our condition becomes C1 should be less than C2. Let's check in which option is this satisfying. First option is saying C1 equal to C2, wrong. In second option, C1 is root 2 times C2. यहाँ तो C1 greater हो रहा है. Third option, C1 is 2C2. Again C1 is greater. Fourth option, C2 is root 2 C1. C2 is greater. So this will be our answer. Chalo. Let's take our next problem. So here we are given a cell reaction. Let's say like this. We are given a reaction like this. Okay. This is a reaction given to us, and we are asked to find E naught of this cell, and we were given equilibrium constant of this reaction as 10 into 10 raised to 50. Kc was given 10 into 10 raised to 15. And we were asked, what is E naught cell? This is also a main PYQ. Direct we can apply relation between K and E. What was our relation if you remember? Log K is equal to NE naught by 0.059. Correct? So just let's substitute the value. K is given 10 raised to 16. N factor you can see in the reaction is 2. E naught value we have to calculate. So E naught comes out to be log of 10 raised to 16 will become 16 into 0.059 by 2. That is 0.059 into 8. If you take it as 0.6, so this will almost become 0.48 volts. Okay. Next example, let's see. So we are given a cell here M3 plus 10 raised to minus 3 molar salt bridge Ag plus 0.01 molar Ag. And E cell of this cell is given to us as 0.421 volts. Here E cell is already given to us. You are asked E naught of M3 plus 2M and E naught of Ag plus Ag is already given to you 0.8 volts. Give it a try for 1 minute. See if you can write the correct equation here. So here, how we should start the problem? Here, we are not given E naught of one of the half cells. Let's assume it as X, what we have to calculate. And let's apply our standard Nernst equation application. First step, to find out E naught cell. E naught cell will be SRP cathode minus SRP anode. Cathode here is silver half cell, anode is some unknown half cell. So SRP cathode 0.8 volts minus SRP anode X volts. Now let's apply Nernst. But before that, let's write the equations. At cathode, reaction will be Ag plus I electron goes to Ag. At anode, the reaction will be M goes to M3 plus 3 electrons. Overall reaction, when you will add these two, you will have to balance the electrons. So for that, the overall reaction will become 3Ag plus M goes to M3 plus 3Ag. So now, Nernst E cell will be equal to E naught cell minus 0.059. And as you have balanced the reaction, you have made 3 electrons on both cathode and anode. So N factor will become 3 log of, let's write, silver ion active mass, silver atom, a solid, active mass 1. M3 plus molarity is given 10 raised to minus 3 upon this M is solid, Ag plus molarity is 10 raised to minus 2 and its stoichiometric coefficient is 3. So Q. And what is E cell given to us already? E cell is given to us 0.421. So 0.421 is 0.8 minus X. This let's take around 0.06 by 3. So 0.02 into this overall will become 10 raised to minus 6. So 10 raised to plus 3 ka log. So that is 3. So that is 0.8 minus X minus 0.06. So X comes out to be 0.74 minus 0.421. So that will be 0.319. So next example, let's take this one. So let's say we are given a cell like this, platinum H2 1 bar, H plus 1 molar, salt bridge, M4 plus, comma M2 plus PT. So this is cell notation given to us. E cell is given 0.092 volt and M2 plus upon M4 plus is given 10 raised to x. E naught of M4 plus 2M2 plus. This E naught value is given to us as 0.151 volts, and we have to find the value of x. You can see how many problems on Nernst are coming continuously. Same application of Nernst again and again. First step, to find E naught cell. This is cathode, this is anode. Cathode E naught value is given 0.151. Anode is hydrogen electrode. And for hydrogen electrode, you know, E naught value by convention we have defined to 0. ठीक है? तो 0.151 minus 0. That is 0.151 volt. E cell लिखने के लिए, for writing E cell, let's write the reactions. तो anode reaction, H2 goes to 2H plus 2 electron. Cathode reaction, M4 plus 2 electron goes to M2 plus. So N factor is 2. E cell is given 0.092 is E naught cell 0.151 minus 0.059. N factor is 2 log of. Products क्या क्या है? M2 plus H plus square, reactants M4 plus into partial pressure of hydrogen. So what this equation becomes is 0.151 ko let's bring on this side. So how much will be left? Subtracting 0.092 minus 0.151 is equal to minus 0.0295 log of H plus and H2, they were given 1. So this will be left this only, M4 plus. Clear? So how much will this become? Negative 9. 059. So this whole cancels, giving me 2. So M2 plus upon M4 plus is 10 raised to 2. That's what you needed to find. The value of x. X will be 2. Okay. Chalo. Another similar problem on permanganate as we were discussing. Just 1 minute. So this was also a very interesting problem in mains. We can see this. We were given reduction voltages. So standard reduction voltages potential for MnO4 minus Mn2 plus 1.51 Cl2 Cl minus 1.36 Br2 Br minus 1.07 and I2 I minus 0.54. So you are asked at pH equal to 3, MnO4 minus will reduce, will oxidize, and the options given to you were here. All Cl minus, Br minus, I minus. Option B, Br minus, I minus. Option C, Cl minus, Br minus. And option D, I minus only. Again, we were first given E naught value, standard values. Standard values, so you know, are applicable only when all active masses are 1. But here, problem is asking at pH 3. pH 3, as you can see in these half reactions. First one we have discussed depends on pH. And what was the reaction of first cell? MnO4 minus plus 8H plus 5 electron gives Mn2 plus 4H2O. So Nernst apply, if we apply Nernst here, E will become 1.51 minus 0.059 by 5 log of 1 by 10 raised to minus 3 raised to 8. That is 1.51 minus 0.059 by 5 into 24. Okay. So let's calculate this value. How much will this value come? So this value is coming 1.22 roughly. 1.22 or 23 we can take. 1.23 ले लेते हैं. Let's take around. So this is coming 1.23. Now you are asked, out of these three, at pH 3, permanganate will oxidize which of them? So basically, the cell here we want, permanganate should get reduced and one of them should get oxidized. Now these will act as anode and this will act as cathode. So for Cl minus, what will be E cell? SRP cathode. Cathode is permanganate. So 1.23 minus reduction voltage of chlorine. Similarly, for Br minus, what will be E cell? 1.23 minus 1.07. And for I minus, E cell will be 1.23 minus 0.54. So what we can see here, this value is negative. These both are positive. Now for a reaction to be spontaneous, we know delta G should be negative. And for delta G to be negative, E cell should be positive. And we are getting positive E cell only for bromine and iodine. So our answer here will become B. Let's take a few numerical type also. So next example I will take like this. Platinum H2 1 bar H plus Cu2 plus Cu. This is the cell given to us, and E cell is given 0.31 volts. pH of the solution is given 3. And you are asked what is concentration of Cu2 plus. It is given like this, 10 raised to minus x. We have to find value of x, and E naught of Cu2 plus Cu is given to us 0.34. So this is the data given to us in the problem. Again, take 2 minutes, try to write a equation. Let's see now, are you comfortable in applying Nernst equation? Okay, let's see now. E naught cell, cathode is copper half cell, anode is hydrogen half cell, and E naught value of hydrogen half cell we know is 0. And copper half cell we are given 0.34. So this is E naught cell. Reactions at cathode and anode. Cathode reaction, anode reaction, let's write. H2 goes to 2H plus 2 electron. Cu2 plus 2 electron goes to Cu. Now let's apply Nernst. E cell is already given to us 0.31 volts. E naught cell is 0.34 minus 0.06. N factor we can see is 2 log of product solid copper active mass 1 H plus, pH is given 3, so H plus molarity will be 10 raised to minus 3 and stoichiometric coefficient is 2. So 10 raised to minus 3 square. Then reactant side hydrogen gas is given at 1 bar. So here Cu2 plus is left. Let's solve this. Bringing this side here. So this will become minus 0.303, sorry, is minus 0.03 log of 10 raised to minus 6 by Cu2 plus. So this cancels out and it becomes 1. So our equation is log of 10 raised to minus 6 by Cu2 plus is 1. So removing log 10 raised to minus 6 by Cu2 plus concentration is 10. So Cu2 plus concentration is 10 raised to minus 7. So our answer for X will be 7. Okay. The next numerical, let's take on Nernst. So we were given a cell like this. Cu solid plus Sn2 plus 10 raised to minus 3 molar is going to Cu2 plus 10 raised to minus 2 molar and Sn. This reaction is given and we are asked delta G for above reaction is given in the form delta G of above reaction is minus X into 10 raised to minus 1 kilojoule per mole. We have to find the value of X. And E naught values are given to us. E naught of Cu2 plus Cu 0.34 volt and E naught of Sn2 plus Sn minus 0.14 volt. So here we are asked delta G calculation. Nernst apply karna, we will have to apply Nernst and then the relation for delta G. 2 steps, but approach still will remain same. First, E naught cell. What is cathode here? Instead of notation, they have given you reaction. That is also same thing. From reaction, you can see which thing is getting oxidized and which thing is getting reduced. Copper from 0 to +2 is getting oxidized and oxidation occurs at anode. So copper half cell is an anode. Tin from +2 is going to 0. It is getting reduced. So tin half cell is cathode. So E0 cell will be SRP cathode minus SRP anode. So these values minus 0.14, minus 0.34. So E0 cell is minus 0.48 volts. Okay. Now, once we have got E cell, next we will calculate this was X only. Next we will calculate E cell. E0 cell we have got. So E cell will be applying Nernst minus 0.48 minus 0.059 and let's write the reactions. The reaction anyway is written and we can see n factor is 2. Log of product molarity 10 raised to minus 2, reactant molarity 10 raised to minus 3. So this will become 10. Log 10 is 1. So this becomes minus 0.48 minus 0.303. Let's say. So this will become minus 0.51. This is E we have got. Now we have to calculate delta G. So delta G will be minus NFE. N is 2. F we know 96500 and E is coming minus 0.51. So how much will this become? It becomes roughly in kilojoules. Joules. So kilojoules it will be 98.43 kilojoules. You have to write in order of 10 raised to minus 1. So that is 984.3 into 10 raised to minus 1 kilojoules per mole. Done? Okay, good. Next example, let's take a pH calculation problem. So let's take a problem like this. PT H21 bar H plus Cu2 plus Cu. There you are given E cell as 0.576 volts. This is EMF of the cell given. You are asked pH of the solution and E naught of Cu2 plus Cu 0.34 volt. It is a very similar problem. Try to give it a try. Attempt to write the equation. So, E naught cell here will be cathode is copper, anode is hydrogen. 0.34 minus 0. E naught cell is 0.34. Reactions. Anode, this will be the reaction. Cathode, this will be the reaction. So let's apply Nernst. So 0.576 is 0.34 minus 0.059 by 2 log of H plus ions. We don't know. We have to find their molarity. Second product here is solid copper, active mass 1. H2 gas, 1 pressure. Cu2 plus 10 raised to minus 2. Okay. So let's try to simplify. Let's bring this here. So this will become 0.236 is 0.06 by 59 ही रहने दो. Let it by 2 log of H plus square by 10 raised to minus 2. Or you can write it like this. H plus 10 raised to minus 1 whole square. This square you can bring out of log and cancel. So you will get 0.236 by 0.059 is minus log H plus by 10 raised to minus 1. This is 4. So log of H plus by 10 raised to minus 1 is minus 4. So H plus by 10 raised to minus 1 is 10 raised to minus 4. So H plus is 10 raised to minus 5. So pH value is 5. Just quickly go through it and see if you were doing the same equation, writing the same equation. So I think Nernst we have understood how to apply. very comfortably. Now you can do all the PYQs and from mains and also NCERT all problems related to Nernst. One more thing in galvanic cells which we should discuss is what happens if I add two oxidation or two reduction reactions. See, a galvanic cell is formed by adding one reduction and one oxidation reaction, a redox reaction. But what will be the operations, the value of EMF if I add two oxidation or two reduction reactions? Like for example, let's take this situation. Fe3 plus I electron goes to Fe2 plus. And let's say E naught SRP is standard reduction voltage of this is, let's say, some value A. And you are given another half reaction, another reduction reaction. Fe2 plus 2 electrons go to Fe. And E naught SRP of this reaction is, let's say, given B. You are asked to add these reactions. Add these reactions and then the reaction you get like this. Fe3 plus 3 electrons goes to Fe. And you are asked what is the SRP value of this half reaction. Now in this case, remember, you can never add or subtract the E naught values. When two oxidation or two reduction reactions are being added, you can never add or subtract E naught values. Here you will have to go by delta G naught. So we know the relation. Delta G naught is minus NF E naught. So what we will do? We will find delta G naught for both of these reactions. Let me call this as delta G1 naught. So delta G1 naught, N factor is 1 for this reaction and E naught is A. So delta G1 naught for this reaction will be minus Fa. And for the second reaction, N factor is 2. So delta G2 naught will be minus 2Fb. So adding the overall delta G naught of this reaction, when we add two reactions, whatever they may be, one oxidation, one reduction, or two reduction, or two oxidation, in any situation on adding reactions, we can always add delta G naught. So delta G naught value is always additive. So now if I add delta G naught for both of these reactions, minus F I take common and I get A plus 2B. And this is delta G naught of this reaction, whose N factor is 3. So now from this delta G naught, I write this delta G naught as minus NF E naught minus F cancels out, and N factor of this reaction, third reaction, is 3. So from here you can see what will this E value come. The E value of this will come A plus 2B upon 3. So whenever we have to add two oxidation reactions or two reduction reactions, we will never add or subtract E naught values. We will only add delta G values. Okay. Let's take an example on this. So let's take a mains PYQ only. So you are given SRP values, some SRP values you are given, E naught MnO4 minus MnO2. This value is given 1.68 volts. Then MnO2 to Mn2 plus. This value is given 1.21 volts. And Mn2 plus to Mn, this reduction value is given minus 1.03 volt. You are asked to find E naught of MnO4 minus to Mn. So now here you will have to analyze all these three reactions. You have to understand that all the three reactions data which is given to you, all three are reduction reactions. And don't make that error, add all these three and you will get this answer. No. Whenever we add reductions, we cannot add EMFs. We have to add delta G. So let's write all the reactions. So first reaction, MnO4 minus is getting reduced to MnO2. Let's balance it out. What is the oxidation state of MnO4 minus Mn in MnO4 minus 7 plus 7. And here it is plus 4. So decrease by 3. So I will definitely have to add 3 electrons. Okay. Acidic medium, let's take. So for charge balance, I will have to add 4H plus. And for hydrogen balance, I will add 2 water. So this is the balanced reaction. 3 electrons. And this E naught value is given to me 1.68. So its delta G naught value will become, what will be delta G naught value? G1 naught, let me say, minus 3F into 1.68. ये हुआ फर्स्ट रिएक्शन. सेकेंड रिएक्शन क्या है? MnO2 से we are making Mn2 plus. Oxidation states involved now are +4 and +2. Reduction of 2, so 2 electron. For charge balance, I need 4H plus, and for hydrogen balance, 2 water here. E naught of this is given 1.21 volt. So for this, delta G2 naught minus 2F into 1.21. And the third, Mn2 plus 2 electron goes to Mn. This E naught value is given minus 1.03. So this delta G3 naught, n factor here 2. So 2F into 1.03. So now if I add all these three reactions, what I will get? The overall reaction, MnO4 minus plus 7 electrons plus 8H plus goes to Mn and 4 water. And what will be its total delta G naught? Will be delta G1 naught plus delta G2 naught plus delta G3 naught. So let's add all these three, taking minus F common. This will become 3 into 1.68 plus 2 into 1.21 minus 2 into 1.03. How much will this come? So this is coming 5.4. So this becomes minus 5.4 F. And for the overall reaction, you can see N factor is 7. So this should be minus 7F into E naught. So from here, you get E naught as 5.4 by 7. So roughly 0.77 volts you get. Let's do one more of this type where we have to add two oxidations or two reductions. Let's see this one more problem today. Okay, like this. The problem given to us was like this, that E naught of Cu2 plus Cu is 0.34 volts and E naught of Cu plus Cu is 0.522 volts. You have to find E naught of Cu2 plus 2Cu plus. A similar approach. Let's write the reactions. What are the reactions here? Cu2 plus 2 electron goes to Cu. This E naught is given 0.34. Cu plus I electron goes to Cu. This E naught is given 0.522. And Cu2 plus I electron goes to Cu plus. This E naught you have to find. Let's assume it X. Now you can see if I add second and third reaction, I am getting first reaction. So delta G naught here will be minus 2F into 0.34. This delta G1 naught, how much? Delta G1 naught and factor 1 minus F into 0.522. And this delta G2 naught, again n factor 1 minus F into X. So we can see delta G naught will be equal to delta G1 naught plus delta G2 naught. So minus 0.68F is minus 0.522F minus Fx. So let's calculate, let's cancel out minus F throughout the equation. So 0.68 is 0.522 plus X. So X from here we get 0.68 minus 0.522, that will be 0.158. So this much part, I think if you do completely, your galvanic cell part of electrochemistry will be done for mains. So bye everybody.